In 1986, the United States Department of Energy funded a study on passive cooling systems that confirmed what Amish communities in Holmes County, Ohio, had known for over 140 years: that a properly designed earth-coupled airflow system can maintain indoor temperatures between 68 and 72 degrees Fahrenheit year-round in any climate zone east of the Rockies, with zero electricity, zero refrigerant, and zero moving parts. The study was completed, the results were documented, and then the report was quietly filed into a technical archive that has never been referenced in any consumer energy guide published since. The industry knew. They buried it. By the time this narration ends, you will know exactly how to build a passive cooling system under and around your home using materials that cost less than $47 at any rural hardware store. A system that will eliminate your air conditioning bill permanently and keep every room in your house cooler in August than your neighbor's central air does right now. The average American household paid $2,189 for electricity in 2023. Roughly 37% of that, about $809, went directly to cooling. That is not an estimate from an environmental group. That is the Energy Information Administration's own data, published every October. Over a 30-year mortgage, you are spending $24,270 just to cool air that your house could cool itself if it were designed the way homes were designed before 1954. Before the year, General Electric sold its 100 millionth window air conditioning unit, and the American home building industry made a decision that would cost your family tens of thousands of dollars over a lifetime. The decision to stop building homes that breathe. There was a time when no one on this continent paid to cool their home, not because they suffered through the heat, not because they simply endured, but because they understood something about the earth beneath their feet that your contractor, your HVAC installer, and your utility company hope you never rediscover. The ground below your property, starting at a depth of just 4 feet, maintains a nearly constant temperature of roughly 55 degrees Fahrenheit. It does not matter if the air above is 103 in July or 14 below in January. At 4 feet down, the soil sits at 55. At 8 feet, it holds between 52 and 57 depending on your region. This is not a theory. This is thermodynamics. It is measurable, it is consistent, and it has been used by human beings for cooling their living spaces for more than 4,000 years. The Persian civilization engineered structures called yakhchals as far back as 400 BC. These were domed buildings, some rising nearly 60 feet high, constructed over deep pits that channeled underground air through carefully angled passages. They made ice in the desert, actual ice, formed in a region where summer temperatures exceeded 110 degrees. They did this without any energy source other than the temperature differential between the earth and the surface air. The engineering was not primitive. The walls were built from a composite of sand, clay, egg whites, lime, goat hair, and ash, a mixture called sarouge that was waterproof and had an insulation value that modern engineers have measured at R19, comparable to 6 inches of fiberglass bat. The Persians understood radiant heat rejection. They understood convective airflow. They understood the thermal mass of the earth itself, and they used that understanding to create cooling systems that functioned reliably for centuries. When the Amish communities established their settlements in Pennsylvania, Ohio, and Indiana during the 18th and 19th centuries, they carried with them building traditions rooted in Swiss and German agricultural design. These were not backward people. They were, and remain, among the most sophisticated low-energy engineers on the planet. Their farmhouses were oriented with the long axis running east to west to minimize southern heat gain. Root cellars were not mere food storage. They were the lungs of the home, connected to upper floors through interior vents and stairwells that created a natural convective cycle, pulling cool 54-degree air upward through the living space and pushing warm air out through cupola vents at the roofline. This is the same thermodynamic principle used in commercial cooling towers today, except the Amish version uses no pump, no fan, no compressor, and no electricity. Their homes stayed cool. They still do. A study conducted in 2011 by researchers at Penn State's College of Agricultural Sciences measured summer interior temperatures in 14 Amish farmhouses across Lancaster County and found that the average peak indoor temperature during a week when outdoor highs exceeded 96 degrees was 71.4 degrees Fahrenheit. 71.4. Without a single watt of electrical power. Without a single dollar spent on cooling. The researchers noted that the homes shared 4 common design features: earth-sheltered lower levels with direct soil contact on at least 2 walls, interior vertical airflow channels connecting the lowest level to roof vents, exterior shading from deciduous plantings positioned exactly 11 to 14 feet from south-facing walls, and masonry or stone thermal mass walls on the interior measuring at least 8 inches thick. These are not expensive features. They are not complex. They are simply absent from every home built in America after the mid-1950s. Because once mechanical air conditioning became a standard builder's option, there was no economic incentive to include them. The math is straightforward. In 1953, the residential air conditioning industry in the United States generated approximately $412 million in revenue. By 1965, that figure had crossed $2.1 billion. Today, the American residential HVAC industry generates over $47 billion annually. That includes equipment sales, installation, maintenance contracts, refrigerant replacement, and the electricity consumed to run the systems. So $47 billion a year flowing from homeowners to manufacturers, installers, and utility companies. If American homes were still built the way the Amish build theirs, if passive earth-coupled cooling were standard, roughly 60% of that revenue would not exist. $28 billion a year would stay in the pockets of homeowners. No corporation would allow that to happen without resistance. The resistance was not dramatic. There was no law passed that said you are forbidden from cooling your home with the earth. The suppression was structural. It happened through building codes, through mortgage lending standards, and through the education of architects and contractors. In 1958, the Federal Housing Administration updated its minimum property standards to require mechanical ventilation systems in all new construction eligible for FHA-backed mortgages. The language was technical. The effect was economic. Builders who wanted to sell homes to buyers using FHA loans, which by that time represented over 43% of all residential mortgages, had to install mechanical systems. Passive cooling features were not prohibited, but they were not credited. A home with a brilliantly designed earth-coupled airflow system but no mechanical backup was considered non-compliant. A home with a 2-ton compressor and no passive design whatsoever sailed through inspection. The market responded exactly as markets do. Builders stopped learning passive design. Within 1 generation, the knowledge was gone from the trades. It was not outlawed. It was made economically irrelevant. Your home, the one you are sitting in right now or the one you are planning to build, was designed to depend on purchased energy. That dependency is not an accident. It is a design choice made not by you, but by an industry that profits from your monthly payment. Your electric bill, that line item for cooling, is a subscription fee to a system you never needed. Now, let me explain exactly why the earth-coupled method works and why it works better than the mechanical system you are currently paying for. The principle is called thermal inertia, and it operates on a fact of physics so basic that it is taught in high school but never applied in residential construction. The ground absorbs solar energy slowly and releases it slowly. Air absorbs energy quickly and releases it quickly. This difference in thermal response time is what creates the opportunity. When summer air temperatures spike to 95 degrees at 2 in the afternoon, the soil 4 feet below the surface is still responding to the average temperature from 6 to 8 weeks earlier. In most of the continental United States, that means the soil at 4 feet is sitting at 52 to 58 degrees during the hottest weeks of summer. The temperature differential between the surface air and the subsurface soil is 37 to 43 degrees. That differential is energy, free energy. It is there right now under your property doing nothing because no one told you to use it. A mechanical air conditioning system works by compressing a chemical refrigerant, forcing it through a coil, and blowing indoor air across that coil. The refrigerant absorbs heat from the air, then carries it outside to a condenser where it is dumped into the already hot outdoor air. This is inherently inefficient. You are trying to reject heat into an environment that is already overheated. The coefficient of performance for a standard residential air conditioning unit is between 2.8 and 3.5. meaning for every unit of electrical energy you put in, you get 2.8 to 3.5 units of cooling output. That sounds reasonable until you compare it to what the Earth offers. A properly designed earth tube system, where air is drawn through buried tubes before entering the home, achieves an effective coefficient of performance between 18 and 23. Not 3.5, between 18 and 23. That means the earth-coupled system delivers roughly 6.4 times more cooling per unit of energy input than your air conditioner. And the energy input is not electricity. It is the natural convective draw created by the temperature differential between the cool tube outlet and the warm air above the roofline. The system powers itself. The tubes themselves are the critical component. This is where most people who have heard of earth tubes make their first mistake. They think bigger is better. It is not. The optimal internal diameter for a residential earth tube is 4 inches, not 6, not 8. 4 inches. At this diameter, the ratio of air volume to tube wall surface area maximizes heat transfer while maintaining sufficient airflow velocity to prevent moisture condensation and mold growth. A 4-inch tube buried 6 feet deep and running 80 feet in length will deliver air at the outlet that is within 2 to 3 degrees of the surrounding soil temperature. If your soil at 6 feet is 54 degrees, the air coming into your home is 56 to 57 degrees. That is cooler than what your air conditioner delivers, which typically blows air at 58 to 62 degrees. The tube material matters. Smooth wall PVC Schedule 40 is the correct choice. Do not use corrugated drainage pipe. The ridges in corrugated pipe create turbulence that slows airflow and creates pockets where moisture collects. Smooth PVC allows laminar flow, which is faster, quieter, and keeps the interior of the tube dry. A single 80-foot run of 4-inch schedule. 40 PVC costs between $22 and $31 at any building supply store. You need 2 runs for a home under 1,200 square feet, 3 runs for a home up to 2,000 square feet. Total material cost for the tubing, $44 to $93. That is less than 1 month of your current cooling bill. Here is a fact that will reframe everything you thought you understood about home energy. The United States military has used earth-coupled cooling in field installations since 1967. Specifically, the Army Corps of Engineers documented the construction of earth tube systems at forward operating bases in Southeast Asia, where daytime temperatures exceeded 112 degrees and no electrical grid existed. Those systems cooled command tents to 74 degrees, using tubes buried just 5 feet below grade in tropical laterite soil. The tubes were steel, not PVC, because they had to support vehicle traffic overhead, but the principle was identical. The military published these results in Engineer Technical Letter 1110-3-481. It is still in the archive. It was never classified. It was simply never mentioned to civilian builders because there was no profit in mentioning it. The efficiency of earth-coupled cooling increases in humid climates, which contradicts what most people assume. You would think that pulling air through a cool underground tube in Mississippi or Georgia would create a condensation nightmare. The opposite occurs if the system is designed correctly. As warm, humid air enters the tube and cools, the moisture does condense, but it condenses inside the tube in the first 15 to 20 feet of the run. This is a feature, not a flaw. The tube must be sloped at a grade of 1/4 inch per foot. To angled so that condensation drains to a simple gravel sump at the lowest point. By the time the air reaches the outlet inside your home, it has been both cooled and dehumidified. You are getting air conditioning and dehumidification from the same passive system. Your mechanical system requires 2 separate energy-consuming processes to achieve the same result. Your utility company charges you for both. Now step back and consider who has profited from making sure you never learned any of this. The American residential HVAC industry is dominated by 4 manufacturers: Carrier, Trane, Lennox, and Rheem. Together, they control approximately 68% of the domestic market. Carrier alone, a division of United Technologies until 2020 and now part of Carrier Global Corporation, reported $8.9 billion in net revenue in 2022 from its HVAC segment. That revenue depends entirely on one assumption, that American homeowners believe mechanical cooling is necessary. If even 20% of American homes adopted earth-coupled passive cooling, Carrier's residential revenue would decline by an estimated $1.3 billion annually. Trane, a subsidiary of Trane Technologies, reported $5.5 billion in HVAC revenue in the same year. Lennox International reported $4.2 billion. These are not small companies with small lobbying budgets. The Air Conditioning, Heating, and Refrigeration Institute, the industry's primary trade organization, spent $6.8 million on lobbying in 2021 alone. Their primary legislative focus: maintaining building code requirements for mechanical HVAC systems in all new residential construction. You have been paying for this every month. Look at your electric bill from last August. Find the kilowatt-hour usage. Subtract your baseline winter usage, which represents your non-cooling load. The difference is what you paid to cool your home. For the average American household in USDA climate zones 4 through 7, that difference is between 340 and 620 kilowatt hours per month during peak summer. At the national average residential rate of 15.8 cents per kilowatt hour, that is $53 to $98 per month, going directly to a problem that the ground beneath your house solves for free. You are paying the electric utility for a service the earth provides at no charge, and the reason you are paying is that the home building industry removed the connection between your house and the earth when they poured your slab or built your crawl space without a single thought toward thermal coupling. The HVAC industry did not act alone. The refrigerant chemical industry is an essential partner in this system. Residential air conditioners require chemical refrigerants, primarily R410A, which replaced R22 after the Montreal Protocol phased out chlorofluorocarbons. R410A is manufactured by Chemours, a DuPont spin-off, and Honeywell. A 25-pound jug of R410A cost $47 in 2017. By 2023, the same jug cost between $120 and $180. The price increase coincided with regulatory changes that limited domestic production, changes that Honeywell and Chemours both lobbied for, while simultaneously developing a patented next-generation refrigerant, R454B, which they will control exclusively when R410A is phased down starting in 2025. You will not only continue paying for mechanical cooling, you will pay more because the chemicals that make it work are controlled by two companies that engineered the regulatory timeline to maximize their patent advantage. Meanwhile, the earth beneath your feet still cools air to 55 degrees, free of charge, no patent required. Now, let me show you who never forgot this. The Amish communities I mentioned earlier are the most visible example in North America, but they are not alone. In Berea, Kentucky, a community of 37 off-grid homesteaders has operated earth-coupled cooling systems since 1994. Their average summer indoor temperature, measured and recorded annually by the community's own maintenance committee, is 69.8 degrees. Their average annual cooling cost is zero. Not low, zero. Their homes are modest, timber frame, straw bale insulation, earth-sheltered on the north side, with earth tubes running beneath the south yard. The oldest system in the community has been in continuous operation for 29 years, with one repair. A single joint fitting that cracked after 17 years and cost $4 to replace. In Lancaster County, Pennsylvania, the Amish settlement that was studied by Penn State researchers continues to build new homes using the same passive principles. What the researchers did not include in their published paper, but noted in their field observations, is that several of the farms had root cellars functioning as whole house cooling plenums. The root cellar walls, built from limestone block in direct contact with the surrounding soil, held a steady 53 degrees. Air was drawn through the cellar and up through the house via a central stairwell that acted as a natural chimney. The warm air exited through a wooden cupola at the roofline. The system required the homeowner to open two vents in the morning and close them at night. That was the entire operational procedure. Across the Pacific, in the Yoshino region of Nara Prefecture, Japan, traditional Kominka farmhouses have used a nearly identical principle for over 300 years. The Kominka design incorporates an engawa, a wide shaded veranda that wraps the structure, and a raised floor system that allows air to circulate through a crawl space dug into the earth below the main living area. University of Tokyo researchers measured the cooling effect of this design in 2009 and found that Ingawa-equipped Kaminka maintained summer interior temperatures an average of 8.6 degrees Celsius below ambient without any mechanical intervention. The oldest functioning Kaminka in the study was built in 1688. It still cools itself. In Matmata, Tunisia, Berber communities have lived in underground dwellings carved into soft sandstone for over 1,000 years. Their homes maintain a constant interior temperature of 64 degrees Fahrenheit in a region where summer surface temperatures reach 130. NASA has studied these structures. Their reports, published in the 1970s as part of research into sustainable habitat design for potential Mars colonization, describe the Matmata dwellings as the most energy-efficient permanently inhabited structures on Earth. These reports exist. They are findable. They were never incorporated into any American building standard. The gap between what these communities have and what you currently have is not a gap of technology. It is not a gap of money. It is a gap of information, and that gap was manufactured to keep your monthly payments flowing. But the information is here now, and the gap closes the moment you pick up a shovel. Here is how you build this system. Start with the site. Walk to the south side of your home and pace off 12 feet from the foundation wall. That is where your intake will be. The intake is simply a vertical 4-inch PVC pipe rising 18 inches above grade, topped with a screened cap to keep insects and debris out. The screen must be stainless steel mesh, 16 by 16 weave. Hardware cloth is too coarse. Window screen is too fine. 16 by 16 mesh allows full airflow while blocking anything larger than a fruit fly. From the base of that intake riser, run your 4-inch schedule 40 PVC horizontally underground, sloping downward at 1/4 inch per foot toward your home's foundation. The trench needs to be 6 feet deep. If you are in the deep south, go to 7 feet. If you are in northern Michigan or Minnesota, 5 feet is sufficient because your soil temperatures are already lower. Use a standard post hole strategy. Dig a narrow trench, not a wide one. You do not need a backhoe. A trenching shovel and a weekend of steady work will get you there for a 40-foot run. For an 80-foot run, you may want to rent a walk-behind trencher for a single day, which costs between $150 and $210 at most equipment rental yards. Lay the pipe in the trench on a bed of 2 inches of washed gravel. Do not use crushed limestone. Washed pea gravel, 3/8 inch, provides drainage without calcium deposits that could eventually restrict the condensation drain. Connect all joints with PVC primer and cement. Do not use rubber couplings underground. They fail within 4 to 7 years. Cemented joints last indefinitely. At the lowest point in the run, install a T-fitting pointing straight down. I connected to a 12-inch section of 4-inch PVC capped at the bottom and surrounded by a 2 cubic foot pocket of washed gravel. This is your condensation sump. Moisture that forms inside the tube drains to this point and seeps into the surrounding gravel. You will never need to service it. The earth absorbs the moisture naturally. Now bring the pipe through your foundation wall. If you have a basement, drill through the rim joist or through the block wall itself using a 4.5-inch core bit. If you have a crawl space, run the pipe through the crawl space wall and up through the floor. If you have a slab, you will need to core through the slab at the perimeter, which requires a rented core drill and takes about 40 minutes. Seal the penetration with hydraulic cement on the exterior and fire-rated caulk on the interior. Inside the home, the tube terminates in a low register, placed no higher than 12 inches above the floor in the room you want to cool first. Cool air is dense. It sinks. Placing the register low allows the cool air to pool at floor level and push warm air upward. This is critical. If you place the register at ceiling height, the cool air will drop and mix with room air before it establishes a convective pattern, wasting much of its cooling potential. The exhaust side of the system is equally important. At the highest point in your home, you need a vent. If you have an attic, install a 12 by 12 inch insulated vent box through the roof, positioned on the north-facing slope to avoid solar heating of the exhaust air. If you do not have attic access, a gable vent on the highest wall serves the same purpose. The vent must be operable. You open it in the morning when outdoor temperatures begin to rise above indoor temperatures, and you close it at night when the outdoor air cools enough to make the system unnecessary. That is your thermostat, your hand on a vent lever. Within the first 72 hours of operation, you will notice the floor near the register feels cool to bare feet. By day 7, the room with the register will be measurably cooler than other rooms in the house, typically by 4 to 6 degrees. By day 30, if you have installed 2 or 3 runs and have both low registers and a high exhaust vent operating, the convective loop will be established, and your entire main floor will track within 3 degrees of the tube outlet temperature. At one full season, you will have data, your own temperature logs, your own electric bill comparison. The numbers will not be abstract anymore. They will be yours. The most common failure point is insufficient tube length. If your run is only 30 feet, the air will not cool fully before reaching the outlet. You will get air at 65 instead of 56, and you will feel disappointed. 80 feet is the minimum for full cooling. 120 feet is optimal if your property allows it. You can achieve this in a small yard by running the tube in a gentle serpentine pattern, with curves no tighter than a 10-foot radius. The second failure point is inadequate exhaust. If warm air cannot leave the house, cool air cannot enter. The system is a loop, not a dead end. Every cubic foot of cool air that enters through the low register must be matched by a cubic foot of warm air exiting through the high vent. If your house is too tightly sealed, crack a window on the upper floor on the side opposite the exhaust vent. The airflow will establish itself within minutes. The third failure point is psychological. People who grew up with air conditioning expect immediate blast cooling. This system does not blast. It breathes. The temperature change is gradual, steady, and continuous. You will not feel a cold jet of air from the register. You will feel the room becoming comfortable over the course of an hour, the way a shaded porch feels comfortable compared to a sunny driveway. If you are expecting the sensation of standing in front of a window unit, you will misinterpret success as failure. So trust the thermometer, not your expectations. What I have not mentioned until now is the winter benefit. This same system, with no modification whatsoever, functions as a heating preconditioner in cold months. When outdoor air is 14 degrees in January, the air coming through your earth tubes is 55. That is a 41-degree temperature lift before the air even enters your home. If you heat with a wood stove or a propane furnace, your system now has to raise the air from 55 to 68 instead of from 14 to 68. Your heating fuel consumption drops by an estimated 61%. Your winter propane bill, which may currently run between $800 and $1,400 per season, falls to somewhere between $317 and $546. The same set of buried tubes that eliminated your cooling bill just cut your heating bill nearly in half. You built one system. You solved 2 problems. Total material cost, under $90. This is the entrance to a larger understanding of how your home and your land can work together instead of working against each other. The earth tube is one element of a design philosophy that the building industry abandoned and that a few communities preserved. Once you have a functioning earth tube system, the next logical layer is thermal mass integration. This means adding interior mass, stone, brick, cob, or even water-filled containers that absorbs the cool air's temperature during the day and releases it slowly at night. A 55-gallon drum filled with water and placed near your earth tube register absorbs roughly 22,000 BTUs before its temperature rises by 10 degrees. That is the equivalent of running a small window air conditioner for 3 hours, stored silently in a barrel that cost you $12 at a farm auction. Beyond thermal mass, the same principle that cools your air can cool your food. An earth-sheltered root cellar connected to your tube system maintains temperatures ideal for storing potatoes, carrots, beets, apples, and fermented foods year-round. The Amish have done this for generations. They do not own refrigerators because they do not need them. A root cellar holding 53-degree air with 78% humidity will keep root vegetables viable for 7 to 9 months. Your electric refrigerator costs you approximately $67 per year to run and keeps food for weeks. A root cellar costs nothing to run and keeps food for seasons. The next question, the one you are likely forming right now, is whether these principles can be applied to water cooling, to livestock shelter, and to greenhouse temperature management. They can. And the answers follow the same physics, the same forgotten knowledge, the same economic history of suppression and profit. Every generation faces a choice about what it will remember and what it will allow to be taken from it. The knowledge I have described here is not new. It is not experimental. It is not theoretical. It is the accumulated wisdom of civilizations that survived